Okay, so here's your review. Well, not review of limits. You're learning limits for the first time. So we're going to talk about limits. Limits are not, is there actually a point on the graph? Limits are a behavior of a graph. It's where is the graph headed? The example that I always use is, have you ever been walking up the stairs and you're not paying attention and you get to the top of the steps and you take another step anyway and you stumble and drop everything you're holding and all your friends laugh at you? Yes, okay. That's like a limit. There wasn't another step there, but if there had been, your foot would have landed right on it. It's where you were headed. It's the behavior of the graph. So it's where the graph was headed. So we're going to look at this one right here as an example. Limit as x goes to -2. So we're zooming in on -2, if you will, of this function. If you plug in -2 to that, you're going to get 0 over 0, which is called an indeterminate form. What that means is there is a hole there. Does anyone remember how we get rid of a hole? Or like get rid of that part that's going to make it indeterminate? We're going to factor it. Okay, so the numerator is going to split x plus 2, x minus 1. And the denominator is going to split x plus 2, x plus 5. And so the x plus 2's cancel, and that's because the hole was at -2. And then you can plug -2 into what's left and figure out where the hole in the graph is. So the hole is going to be -2 comma whatever we get when we plug in -2. So let's see, what would that be? This would be -3 over +3, so -1. So you have a hole at -2, -1. I'm not going to make you draw the graph, but just use your imagination. There would be a hole in the graph at -2, -1. And so the limit as x approaches -2 of this function would be -1. There's not actually a point there. There's a hole, it's missing. But it's where the graph is headed. It's the behavior of the graph. Does that make sense? Like if you zoomed in on that point, that's where it's headed. All right, so we're going to fill in this table. I'm just going to grab a copy real quick and watch and follow along. I'm going to go to y equals, and I'm going to type in this function. It's been a while since I've used the calculator. All right, so there's our function. I'm going to go to the table. And we're looking around -2. All right, so -2, it says error because there's a hole there. So here we get an error. And then we're going to zoom in from either side. So let me start at the ends. I've got -2.5 and -1.5. Let me go to my table set. And I'm going to make it count by halves. I'm going to make it count by 0.5. Okay. So at -2.5, we have a -1.4. I know that's blue, so you kind of can't see it, but I'm going to write it here in pencil. It was -1.4. And then at -1.5, we have -0.714. And now we're going to zoom in further. It's like a microscope and you just keep zooming in. So I'm going to go back to the table set. And now I'm going to change it by 0.1. I'm going to count by a tenth and go back to the table. So -2.1, I've got -1.069. And then on this side for the -1.9, we've got -0.935. And then I'm going to do one more. Now we're going to count by 0.01. Do you see how I'm changing the increment to be smaller and smaller and smaller? So this is -1.007 and -0.993. Yes. Truncating. You can do either. I like to truncate because it doesn't involve thinking. which I'm not telling you to be lazy, but in a way, you do want to you want to do the least amount of work possible because there's going to be so many things in this class that are so difficult that when you can make something easier, just do that. What she's talking about is on the AP, you guys remember 3 decimal places? You guys had me for pre-calc, the first 3 that you see, because I tried to get you ready for it then. It's the first 3 that you see. I don't know how to explain this to you, but in an AP exam, if you don't do 3 decimal points, they will not give you. Like if you do 2 decimal points, they just like literally will give you nothing. Like it will be nothing. So shout out some numbers. 3, 9, 4, 1. Let's do that. So if that's what you get, you can either put 3.941. That's called truncating, which is what I suggest because it's the first 3 that you see. You don't have to use your brain. It's just the first 3 decimal points. Or you can round that up. So this is truncating, this is rounding. They will accept either of these. They will not accept this at all. Unfortunately, this didn't show up on the video. He's saying it. I truncate. You have to do 3 decimal points. All right, so here's what the whole point of that was. What are we headed towards on both sides? We have negative 0.7, negative 0.9, negative 0.99. Negative 1.4, negative 1.06, negative 1.007, negative 1, which we already knew. It's just sometimes they want you to see it in a table. So I was like, let's do at least one example in a table. All right, in order for a limit to exist, the same value is approached from both sides. So if we were zooming in on the point and one part of the graph went somewhere and another part went somewhere else, there would not be a limit. I always think of this, as time goes by, the movie keeps getting older and older and older, but have you ever seen Mean Girls? No, you're a bunch of guys. Jenna, have you seen it? Okay. Never mind. There's this scene at the end where she's like one of the mathletes and they go to this competition and she's like, the limit does not exist. Like, anyway. It's funny, I like to bring that up, but if you haven't seen it, just forget that I can't edit the video. All right, so the same value has to be approached from both sides. Your function cannot increase or decrease without bound. What does without bound mean? If something increases without bound, where is it headed? Good, infinity. Or if it decreases without bounds, negative infinity. Now there's an exception to that, except one-sided limits. You can increase or decrease without bound as long as it's only from one side. Like if it's just from the left or from the right, then you can increase or decrease without bound. But if it's both sides, it'll be does not exist. And then last thing, f of x cannot oscillate, which let me type in an example and show you that. This is the graph of sine of 1 over x. Do you see how like right at 0, that if we were doing limit as x goes to 0, do you see how it like looks like a little heartbeat kind of thing? Let me zoom in on it. This is kind of cool what it looks like. It's like, and I'll zoom in again. What it's doing is it's like spazzing out right at 0. And if you zoom in any further, it'll look like a barcode. There's no overall behavior there at 0. Like the graph can't make up its mind. That's called oscillating. So you won't get a limit. All right, so here's our graph. That was me getting through all the like explanation. Now we're going to actually answer some questions, and these are going to go real quick because you pretty much just write the answer. There's no work. So here's our graph. Limit as x approaches -1. I am going to ask you guys a lot of these and see what you remember. And I don't want you to be frightened of getting it wrong. I'm going to tell you all the answers, right? But I want to see what you remember, okay? So here's -1. What you want to do is kind of cover up everything except -1. Where's the graph headed as we zoom in on -1? 0. That's it. That's like literally all that there is to that, right? Limit as x goes to +1. A little bit trickier for that one. What do you guys think? Yeah, you want to cover up everything except 1. So it will be -1. But Ms. Cole, there's a hole there. It doesn't matter. Think about falling up the steps. It's where the graph is headed. If you zoom in on that point, both sides go to -1. All right, limit is x goes to -6. That little plus sign means from the right, from the positive side. If you want to look just at -6, just from the right side, where are we going? Negative infinity. All right, now -6 just from the left side. Negative infinity. -6 overall, though, you can't. Good. That would be does not exist. D-any. You can only have positive infinity or negative infinity as an answer if it's one-sided. And that's because, will these two parts of the graph ever meet? No, they will never touch. All right, this is -2 from the left. All right, so here's -2. Ignore everything except -2. We want to go from the left. I know there's a hole, but it doesn't matter. Where are we headed? Good, that's -1. Now we want to do -2 from the right. So here's -2. We want to go from the right. That's this part right here. Where is that headed? Can we call that 2? I know it's like a little bit above 2. We're happy with 2. Okay. And then -2 overall does not exist. Both sides do not match up. That's called a jump discontinuity. All right, limit as x goes to -infinity. That's this side right here. Where are we leveling off? 0. Limit as x goes to positive infinity. That's the right side of the graph. -2. Do you remember doing end behaviors in algebra 2 and pre-calc? That's exactly what that is. That's all that is. All right, now we want to go to 4 from the left. All right, here's 4 from the left, negative infinity. 4 from the right, positive infinity. 4 overall does not exist, right? -5 from the left. It actually doesn't matter so much that it's from the left, but I'll draw like a point on there a little bit more bold. If we go to -5 from the left, what do you want to call that? Yeah, we can all agree that's -2. Good enough. And then +5, limit is x goes to +5. 0. All right, and then these ones are actual values. It's not behavior now. Now it's, is there actually a point there? All right, so where is the filled in circle? So f of -2 is 2. F of -6, there's an asymptote there, so does not exist. F of 1, a little tricky. Good. The limit as x goes to 1 is -1. The limit is down here, but the actual point is, I call that like, haha, tricked you, stole the point. It's over here now. All right, f of 5 does not exist. F of 4 does not exist. F of 0 is -1, and then f of -1 is 0. Oops, let me move that up. All right, then the next thing we're going to talk about is continuity. So there are 3 rules for continuity at a value C. Now, it's always weird when you write it out and there's not an actual number in there. C in a real problem would be a value like 3 or 7, okay? But the point has to exist. So f of C exists, which should make sense. If you want continuity, there's got to be something there. You can't have a hole. All right, so there is a point, and the limit as x approaches C of the function exists. That means that there has to be agreement in the behavior from both sides. In other words, there can't be a jump, because then there would be a break in the graph. You wouldn't have continuity. So there has to be a point, there has to be a limit, and then they have to equal each other. So the point, f of C, equals the limit as x goes to C of the function. So there has to be a point, there has to be a limit, and they have to equal each other. that ring any bells from last year? Like that 3-part definition? Okay, a point, a limit, they agree. So here are the types of discontinuities, the ways that you could break those rules. So let's break the first rule. How could the point not exist? What's the graph going to look like if there's not a point? A hole or good, an asymptote. All right, so this is if the first rule gets broken. So this is if f of c does not exist, if you don't have a point. And then we label the discontinuities as either removable or non-removable. Do you remember that? Can I talk about that? Removable means you could fix it if you could just put a point back in. Like a point has just been removed, like took a point out of the graph. Do you get what I'm saying? So this would be removable. You could fix it by just putting a point back in. An asymptote is non-removable. That's a more deep-seated issue. You can't fix that graph and make it connect together again just by sticking a point back in. So that's what's called non-removable. All right, let's say we break the second rule. So there would be a point, but there's not a limit. That is going to look like a jump. So something like that. So that's if you break the second rule. And I'm writing this out here, I'm writing every little thing like that it got, like the rule that got broken there. If you can't keep up because I wrote too fast, remember I'm going to post this, the filled in notes and the video, okay? So would that be removable or non-removable? Like, could I fix that by just putting a point back in? It would be which? No, because if I try and put a point back in, yeah, like it won't connect. Yes. Okay, so this would be non-removable. No one else said anything though, so I'm glad you. We're gonna play a game next class with this vocabulary too, so we'll get to practice it. All right, and then if the last rule gets broken, there's a point and there's a limit, but they don't agree with each other. That's this situation. See the points over here now. Na. Yeah, so there is a point and there is a limit. Both sides come to the same place, but they don't agree. So this is when the point doesn't equal, it's like that equal sign, like the no parking sign with the line through, doesn't equal the limit. Yes. That can only be a piecewise function. Yeah. Because you would have to define the rest of the function on a certain domain and then define that point for just that one x value. And so that would be removable. Because if you could put the point back, you could fix it. It's like the point escaped, like go and bring it back. All right, so for these, we're going to use that same graph that was on the other side. What I'm going to do is put this up here so that you guys don't have to keep on flipping your paper over so that you can see it. Okay, so we're going to use this same graph. Now, these are yes or no questions. Are we continuous or not? And if it's a no, we're going to say why. Okay, so let's look at 4. Are we continuous at 4? What do you think? Yes or no? And it's because there's not a point there. F of 4 does not exist. All right, how about -2? No. We have, this one's tricky. We have a point, so there's a filled in point there, but what doesn't exist? The limit doesn't exist. The left side and the right side don't match up. Like if you zoom in on that point, you're not headed to the same place. So limit as x goes to -2 of the function does not exist. This is mainly getting you guys used to the notation. Go ahead. I was waiting until someone brought that up because I don't like to go in a direction if no one brings it up because then I'm scared I'll confuse people. You could also say, what he's bringing up is you could also say for x equals 4 that the limit does not exist. So either one is acceptable, and this one's just easier to write. But I would obviously accept either answer because they're both true. All right, how about at 3? Are we continuous at 3? Yes. Which is cool because then you don't have to write anything. All right, how about -6? No. And kind of the same thing here. You can either say f of -6 does not exist, or the limit as x approaches -6 of the function does not exist. This is shorter though. And again, I'm not telling you to be lazy, I'm telling you to be efficient. It's just the shorter way to write. All right, how about 5? No. And why not? Yeah, we don't have a point at 5, but that's going to be a reason coming up. So just, I know, because you guys, it's up here. I know, I'm sorry. Yes, exactly. What Jack just said, everybody. There is a limit there, but there's not a point. All right, this is the one Gabe was just talking about. At 1, it's no. There is a point and there is a limit. They don't equal each other. So f of 1, that's the point, does not equal the limit as x approaches 1 of the function. Now these other 4 are intervals. So remember, a parenthesis means you're not including the number. A bracket means that you are including the number. So from 8 to infinity, and it looks like the 8 got tired and fell over. But we're talking about from 8 to infinity is the function. That happens all the time in this room. All right, so from 8 to infinity, from 8 onwards is the function continuous. Yes, you could. The algebra 1 definition is you could trace it without lifting your pencil off the paper. Now we're talking about limits, so you have a bit more grown-up notation to use. But if you can trace it without lifting your pencil, then it's continuous. All right, -5 to -2, and you do not need to include the endpoints. Then yes, so there's a hole there, but we're not including it, so it's okay. Now, if there was a bracket on the -2, we'd have an issue. Thank you for heads nodding. I had none of that last year. Like even just seeing you guys go like this means so much to me. Like I couldn't see my students at all. I just talked into the abyss and like hoped that someone was on the other side. I was like, I'm gonna just keep talking and hope that someone's with me. All right, from 5 to 7, and we do want to include the endpoints. So that's a no. And the problem is f of 5 does not exist. When people go to give a reason for the interval ones, they always think that they have to explain the whole interval. You don't. 1 point not being there is a sufficient explanation. So they're like, but we didn't say anything about 7. You don't need to. 1 point not being there wrecks it. So that's all you have to say. All right, and then -1 to +1, we are including the endpoint. So that's a no, and it's because of this issue. Now, unfortunately, you can't just say f of 1 does not exist, because it does exist up there. It is this exact same reason that we have for number 28. So you can copy that over. I'm just going to add one thing to it. Go ahead and copy it over, and then we're just going to add one small thing to it. So this reason for number 28, I just wrote it all over again. And then just look, just watch, because don't look away or you're going to miss it. The only thing you need to include there is that it's from the left. And the reason why is your interval was from -1 to 1. We're not going beyond 1, so it has to be from the left side. Right, this seems like this is going really well, right? Now we've got these piecewise functions. We want to find p so that the function is continuous. Here's what has to happen. The two pieces of the function have to meet and make friends. Okay, so what are you going to do with them? Set them equal. That's it. It's actually very intuitive. So you're going to set these two things equal. X squared minus 2 equals x minus p. And then you're going to plug in the x value where you want them to meet, which in this case would be -1. And that's given in the problem. And you can see it right here. So that's what we're plugging in for x. So we'll have -1 squared minus 2 equals -1 minus p. You're just plugging that in for x. I actually kind of like these because it's you set them equal, plug in the number, solve. So -1 squared would be +1, minus 2 would be -1, equals -1 minus p. You would add 1 and get 0. And you could say 0 equals -p, but you can't negative a 0. So that one was a little weird. It came out to 0. But you like finished it before I even wrote it down. So, all right, and then same thing with this one. We want the function to be continuous at 4. So you're going to set the two pieces equal. And then plug in 4 for x. Not p. You're plugging in for x. P is what you're trying to find. All right, so let's see. 4 squared is 16. Plus 3 is 19. And then where would we want to go from there? We do want to factor, but first. Were you guys with me when I was like, evacuate, evacuate? Do you remember that? Okay, all my silly, stupid things. Right? Evacuate, get everybody to one side so it all equals 0. So when you subtract 19, that's going to be -15. And then you can factor. And so actually, we're going to get 2 answers for this one, which is kind of cool. So what is that going to be? P minus 5 and P plus 3. So we get 5 and we get -3. Do we need another 2-minute break before I do the squeeze theorem, or do you want to just like push through and finish that? I know you're probably fading because like you can handle it. Okay. Squeeze theorem frustrates me because it's something that's very simple to understand, and you have to write like a paragraph to explain it. It's like taking the simplest thing imaginable and making it as complicated as possible, which is very frustrating to me, but it's liable to show up. So we're going to go through it. Right? It says if h of x is smaller than f of x is smaller than g of x. It's like saying so-and-so is shorter than so-and-so who's shorter than so-and-so. Like there's a baby bear, mama bear, and papa bear. Do you get what I'm saying? Small, medium, large. Okay. And the limit as x goes to c. So limit as x goes to some number of h of x, that's baby bear, small one, is L. Pretend that's some number. And that's also equal to the limit as x goes to c of g of x. That's the tallest one. So if the smallest one and the tallest one head to the same value, then you know the one in the middle also heads to that value. Does that make sense? Like logically that makes sense, right? If the smallest one goes to 7 and the biggest one goes to 7, the one that's stuck in the middle of them is also going to go to 7. Here's a visual of it. H of x would be like the smallest function, that'd be down here. And g of x would be the biggest function, that would be up here. What we're saying is if both of those go towards this value L, like pretend that's L, if f of x is stuck in between them, then f of x also goes to L.
I never understood that it was abstract. I always thought of it in realistic, like real terms.
Yeah.
Like, not mathematically. I could never picture it.
Me too. Does that make sense though? Like a small, medium, and large? And if you don't feel like copying that down again, I'm going to post this on Schoology. It'll be there. But if this function goes here and that function goes here, the one that's stuck in between has to go there too. It's a very simple thing. But then we're going to write a lot for one problem. I'm sorry. Okay. And if you do want to just listen again, I'm going to post it. It's part of the curriculum, so we're going to cover it. So last one. Functions h and g are continuous. Now, if they are continuous, that means there's a point, there's a limit, and they agree. If they throw you that word continuous, you get all that information in that one word. A point, a limit, they agree. H of 5 equals G of 5, which equals 2. So the point 5, 2 is on both of those graphs. F of X is in between them. So it's going to get squished or squeezed in between. On the intervals 3 to 7, that's just in there because 5 is on that interval. Is F of X continuous at 5? Spoiler alert, the answer is yes. You just have to do quite a bit of writing to explain it. All right, so here we go. First, we're going to find that there's a point. Since H of 5 equals 2 and G of 5 equals 2. That's saying since baby bear is this and papa bear is this, we're going to say then mama bear also has to be this. Like the smallest one and the biggest one are then. Anyway, since H of 5 equals 2 and G of 5 equals 2 and which order they go in? H of X is smaller than F of X is smaller than G of X. Since F of X is in between them, F of 5 also equals 2. So since both of these are 2 and F is in between, F of 5 is also 2. Make sense? Okay, so we have a point. That's rule number 1. We got the first thing down. We're good. All right, so since that's true, all right, so since this is our next thing, I'm going to kind of like label these. We'll make like a bullet list. Since, which 2 was it? H of X and G of X are continuous. I'm going to abbreviate continuous. Since they are continuous, we know that their limits are going to equal 2. Limit as x goes to 5 of H of X equals 2. And limit as x goes to 5 of G of X equals 2. Since they're continuous, since they have a point there, their limit is also going to be 2. And so limit as x goes to 5 of F of X has to equal 2. So here's the grand finale. So yes, F of X is continuous at x equals 5. Because we said there was a point, we said there was a limit, and we show that they agree. They're both 2. It's like, what were we trying to prove in the first place? We're trying to prove that the function in the middle, the F of X one is in the middle, is continuous. Yeah, it's like you're trying to prove that the one that's in the middle has continuity. And as long as the other 2 do, that one does as well, which again is a very simple thing, but you have to explain all the rules. There's a point, there's a limit, they agree.